In today's lesson, we're reversing our discussion on collisions to talk about explosions. This is essentially the reverse of when two objects hit each other and stick together, and that we start with one object, so think pieces stuck together, that explode into two pieces going in different directions, at least different velocities. So, for example, a 0.060 kilogram rifle bullet leaves the muzzle with a velocity of 6 times 10 to the 2 meters per second. If the 3 kilogram rifle is held very loosely, with what velocity will it recoil? In other words, it kicks backwards because it pushes the bullet forwards. This is the same idea as Newton's third law. Again, equal and opposite forces means equal and opposite impulses. So when we have one thing stuck together and then things flying off in both directions, we can use our conservation of momentum. Now, kind of a nice corollary when we're holding something is that it starts out with a velocity of 0. So although I'm going to start maybe writing P initial equals P final, momentum initial equals momentum final, or the sum of the initial momentums is the sum of the final momentums. Because that rifle is being held still at the beginning, this side ends up being 0. So it'll save me a little bit of writing if I go 0 equals, and then this is, remember, MA VAF plus MB VBF. Again, taking into consideration directions. So if I know the masses, the 0.060 of the rifle, of the bullet, and the 3.0 kilogram rifle, what am I actually looking for? Well, I have the velocity of the bullet, and I'm looking for the velocity of the rifle. So let's think in terms of A and B. This is A, and this is B, and I'm looking for VBF. This is what I need to solve for. So in order to do that, I would subtract this term to the other side and divide by the mass. So I get VBF equals negative MA VAF divided by MB. And this negative is going to indicate that we're going in the opposite direction of the bullet. So mass of the bullet, 0.060. Velocity of the bullet, 6 times 10 to the 2. I'm just going to write that as 600 just because it's shorter, divided by the 3 kilograms of the rifle. And I forgot the negative. Negative needs to come along because that's going to indicate we're going in the opposite direction. All right, so go ahead and pull out your calculator, and we're going to plug that in. Let me just clear this up. And we're going to type in, here we go, negative 0.060 times 600 divided by 3 gets us an answer of negative 12 meters per second. Or in this case, because my reference frame was the velocity of the bullet is forward or positive, this is 12 meters per second in the opposite direction from the bullet. That's why if you're not careful and you don't hold on to the rifle and it kicks back, it could break your collarbone. However, if you're holding on to it very tightly, then you become part of the system and your mass becomes part of the system. So instead of the rifle stock getting shot back against your shoulder, you are also pushed back at the same time. That's why you need to have the rifle butt stuck straight to your shoulder when you're shooting a rifle. If you're not sure what I'm talking about, go ahead and Google it. Example number 2, Spencer is sitting in a canoe, floating on the water next to a dock. He decides to stand up and step out of the canoe and onto the dock. Why does Spencer get wet? In other words, he stands up, he takes a step, and instead of landing on the dock, he lands straight in the water. What's going on here? Well, in this case, when he's pushing backwards on the canoe, so here he is, he's standing in the canoe, and in order to get out, he needs to push backwards on the canoe, right? In order to move, for the canoe to move forwards allow him to step onto the dock. And instead of pushing him forwards as much as he would normally expect, we end up with the canoe also going backwards. So Spencer just pushes the canoe out from under him, but does not actually move forward as much as he'd like to. In order to see this in action, we're going to take a break and watch the video, Zero Momentum on Water. So I hope that was illuminating as to why Spencer would end up getting wet if he tried to step out of his canoe in example number 2. As you can see, the boy walking along the paddleboard didn't end up going very fast compared to how far he was walking. You may have noticed he did make a little bit of progress forward, but that was actually undone as he went backwards again, and it wasn't nearly as much as he would have if he was just walking on dry land. Anyway, time for another example. Example number 3. A 45-kilogram boy and a 60-kilogram girl are standing in the middle of a frozen pond. So their initial velocity, their standing, is 0. So that means their initial momentum of both of them is 0 as well. Kilogram meters per second for momentum. The boy gives the girl a push as shown, and she moves off with a speed of 2.4. What velocity does the boy move off with? Ignore friction. So if we call this A, this is VAF, this is MA, this would be BBF, and this would be MB. Then I'm looking at, again, we start at 0, so I'm just going to start there. 0 equals MA VAF plus MB VBF. And again, I'm working to solve for VBF, velocity of the boy final. I end up with the same expression as I have up above. VBF equals negative MAVAF over MB. Plug everything in, so I've got negative, mass of the girl is 60, velocity 2.4. In this case, I'm going to call it actually a negative 2.4 because she's going off to the left. And the boy's going to end up going to the right, which we want to be positive. Mass of the boy, 45 kilograms. Again, pull out your calculator. I'm not going to show you it this time. Just go ahead and figure it out for yourself. Negative 60 times negative 2.4 divided by 45. And that gets me 3.2 meters per second. In the context of this question, a positive answer is to the right, which is what I would expect based on the diagram. So there is his final velocity. Now this question continues on the next page, so don't lose sight of this information. Part B, what is the impulse of the boy? Well, I know that impulse is change in momentum, is mass times velocity initial, final, minus mass times velocity initial. In this case, my initial velocity was 0, so this part just kind of goes away, and I've got mass of the boy, which was 45 times the 3.2 that I ended up with. So go ahead and plug that into your calculator, 45 times 3.2, and that will get you 144 kilogram meters per second. Again, thinking in terms of direction, positive answer to the right, and that makes sense. He was going 0 and he increased his momentum to the right, so this is going to be right. There's his impulse. Next part of the question asks, what is the impulse of the girl? Well, we know that the impulse on the boy has to be equal and opposite to the impulse on the girl. That's based on Newton's third law of equal and opposite forces, and also based on conservation of momentum. If the boy's momentum increases to the right, the girl's momentum has to increase to the left, or decrease to the right. In this case, it is increased to the left. So impulse is going to be the same, and you can actually do the calculation for that if you want to. But it should come out, we also get 144 kilogram meters per second, but this time to the left. If you're not sure why that might be, go ahead and actually do this calculation. Plug in the mass of the girl, plug in the velocity of the girl, taking into account velocities left, and that's what we end up with. Last part, if the push lasted for 0.25 seconds, with what average force did the boy push on the girl? So I need to find the force of the boy on the girl. And I'm thinking about this equation, delta P equals F times T. And I'm trying to solve for F. So I've got F equals change in momentum over time is going to be 144 over 0.25. Again, go ahead and plug that into your calculator. And I get 576 newtons. Now I have to think, okay, the force of the boy pushing the girl. Well, the girl was standing still and it ended up going to the left. So the boy is pushing the girl towards the left. The force is going to be left. And this comes from the fact that we're looking at the girl's change in momentum, which actually we could have made negative at this stage if we wanted to. But the force on the girl is to the left. Okie dokie. Example number 4. A 4,000 kilogram space capsule consists of a 2,500 kilogram main capsule and a 1,500 kilogram probe. The space vehicle is traveling at 120 meters per second when an explosion occurs between the capsule and the probe. After the explosion, the probe moves forward at 280 meters per second. What is the new speed of the main capsule after the explosion? So in this case, because I have an initial velocity, this is my v initial, I can't start with 0 equals. That only works if I'm standing still at the beginning of my explosion problem. If I'm not standing still, what happens instead is that the two pieces of my original object are treated as one big piece with one initial velocity. So I could write this as ma vi plus mb vi, if you like, where this would be a, this would be b, a, b, or I can actually factor out the vi to go, this is vi ma plus mb. In other words, I have one big mass that is the combined mass of them together. And this actually works out the best if you're trying to solve for vi. When you're given vi, it doesn't really matter which way you go. And that, of course, is going to be equal to ma VAF plus mb VBF. And what am I looking for in the question? It's asking me for the velocity of a final. With what? How, after the explosion, what's the new speed of the main capsule? So I'm looking for this. So I'm going to subtract off mb VBF and divide by ma to get me VAF equals VI ma plus mb minus mb VBF all divided by mass A. Okie dokie. I think this time I'm going to do this in 2 steps when I plug it into my calculator, just so I don't make any mistakes. So pull out your calculators. Hang on, I'm going to write this down first. So velocity initial of everybody is 120. Mass A, 2,500, plus mass B, 1,500, minus 1,500 times the 140. And all of that is divided by the 2,500. All right, here we go with the calculator. 120 times 2,500 plus 1,500 minus 1,500 times 140. And all of that is divided by 2,500. And that tells me the new speed of my capsule is 108 meters per second. And in the case of this question, I could call this to the right. They say forward, so I could say 108 meters per second forward as being the positive direction. Since they give me a diagram, I'm fine with you also calling forward to be right, if that helps you out. So the capsule is still moving in the same direction as the probe, it's just slowed down and the probe has sped up. We're going to keep going. What is the magnitude of the impulse given to the probe? All right, so again, impulse is mass times change in velocity. or mass times V final minus V initial. Mass of the probe was 1500. V final 140, V initial 120. No negatives in this case because everything's going the same direction the whole time. And so what that ends me up with, this would be a 20 in here. I think this is going to end up being like 30,000. There we go. 30,000 kilogram meters per second. And again, I need 2 sig figs, so I'm going to make this 3.0 times 10 to the 1, 2, 3, 4 kilogram meters per second. There I've got 2 sig figs, and I'm going to call this forward. Same direction. The probe is moving forward. C, what is the magnitude of the impulse given to the capsule? Now I want you to convince yourself that it's going to be the same number, but backward, but a negative. So we're actually going to do the math on that. So delta P equals M delta V mass times V final minus V initial. In this case, we're working with the 2,500 kilograms. And we're going from an initial velocity, again, of 120, but a final velocity of 108. So 108 minus 120, that's where your negative is going to come in, because remember, this is my V final minus V initial, and I can plug that into my calculator. So 2,500, 108 minus 120. And it gives me, again, the negative indicates backwards. So I'm going to call this negative 3 point. Actually, I'm not going to call it negative. I'm just going to leave it positive and write backwards. So 3.0 times 10 to the 4 kilogram meters per second backwards. And you might be asking yourself, wait a second, how can it get an impulse backwards when it's still moving forwards? And the key to that idea is that it has slowed down. It's still moving forward, but it's not going as fast as it used to be, which means they put on the brakes. There was an impulse to the left to slow it down, even though it didn't slow it down enough to make it start going in the other direction. Okay, a few less tangible numerical examples. Example number 5. Mountain climbers use nylon safety ropes due to their tendency to stretch considerably under stress. Use physics to explain why. Actually, this really comes back to the idea of change in momentum equals force times time. This actually has nothing to do with explosions. So maybe pause your video for a moment and think about how that would work out, why you would want to have the rope stretch under stress, and then come back and see if you agree. So again, the big idea here is that no matter whether the mountain climber is caught by a rope or hits the rocks below, his change in momentum is going to be the same. It's going to be from whatever speed he's falling to get to 0. So if the change in momentum is the same, then we're thinking, okay, longer time as the rope is stretching means lower force. So with a nylon rope, more stretch means more time, smaller force, smaller acceleration, much less damage. Example number 6. Why does conservation of momentum explain why it is so difficult for firefighters to hold hoses that are ejecting large amounts of water at high speed? Now this does have to do with the idea of a collision. If you think, okay, here's my firefighter holding the giant hose and water is spurting out of the end. We should have used a different color. There we go. Water is spurting out of the end. What happens to the hose? Well, large amounts of water means high mass, high speed. Again, that's going to be a huge impulse or huge change in momentum. And in that case, again, the idea of the impulse of the water shooting out has to be counterbalanced, equal and opposite direction of the hose shooting backwards. So in order to hold on to it, you have to be able to counter that force in order to keep yourself in one place. Again, this is explosion example, equal opposite momentum. And number 7, the diagram below shows 2 pop cans of unequal mass. So 2 pop cans, but somebody's put some rocks in one of them. Or maybe they put twice as many rocks in that one as that one. They are initially at rest. So this is the nice thing about this question, is that we can say that Pi is 0. We start out with 0. An explosive charge is detonated between them, and the cans fly apart. What can be said about their velocities after the explosion? Well, the first thing that's kind of obvious from the question is their velocities are going to be in opposite directions. But is there anything else we can say about them based on the idea of MB, VBI, no, VBF, whoops, why did I start with B's? MA, VAF plus MB, VBF has to equal 0 because we're starting with an initial momentum at rest. Well, in this case, MA is just going to be M, and MB is going to be 2M. So if I want to figure out how these are related, maybe I can solve for one of them. If I solve for VAF, I'm going to subtract the 2M to the other side. So I'm going to make this MA, VA, whoops, not MA anymore, just M, VAF is equal to negative 2M VBF. And if I divide out the M's, what I get is that, in fact, they are in opposite directions. That's what the negative is telling me. But it's also telling me that the velocity A is twice as big as velocity B. So I'm going to write this down, actually write this out. So the velocities are in opposite directions. And the velocity of M, which was my VA, or my A, is twice the velocity of 2M. So one has twice the mass, therefore it has half the velocity. The other one has half the mass, it has twice the velocity. And that's what allows me to stay at 0. If I want to show this again one more time, this is going to be M. This has to be twice the velocity, is equal to, or plus 2M V, and remember it's twice and opposite direction. That's subtraction. So that needs to cancel out and give me 0. So this is my 2M mass. So velocity is twice as big and in the opposite direction. So that's it for this lesson. Again, the main idea is still conservation of momentum, starting out with that MA VAI plus MB VBI, just taking into consideration the specific case of explosions. Have fun with your homework.